So we have this question. Now, this is a issue that is discussed in 1995 by Harrison and Locke in their article. So what is the difference between specialized serial processing and generalized parallel processing? So these are two options when you need to develop a sequence of tasks that are going to be required to get a service. Now imagine this loan officer and the customers, the clients are arriving for loan application, okay, for loan application. And they are going to each application, each arrival is going through four of these processes sequentially, okay? So they are going to go through a credit check in the first place. Then a loan covenant will be prepared. Then the loan will be priced. Okay, so the interest rate is going to be determined. And then the funds will be disbursed, which means the loan application are going to collect their money and leave the loan office. Okay, so the whole process for any entity consists of these four sequential process. So they are prerequisites of each other. For example, a credit check operation is a predecessor for preparing a loan covenant, which means we cannot start the loan covenant preparation operation before we complete the credit check operation for an entity. So basically we have four consecutive processes that every entity must go through, okay? So let's read the details of the question. So the applications are arriving with exponentially distributed inter-arrival times with mean of 1.25 hours. So we have this parameter here, inter-arrival times follow exponential distribution. This means the arrivals are occurring according to a Poisson process, okay? So remember now, the arrivals are occurring according to a Poisson process. And what is the arrival rate? The arrival rate per hour is equal to 1 over 1.25, which is 0.8 arrivals per hour, which is the reciprocal of this value, 1.25. And 1.25 is the average inter-arrival time. However, in ARENA, when you are introducing the inter-arrival time distribution, you do not write the rate parameter. Instead, you write the average inter-arrival time for the exponential distribution. Please do not forget about this. So we do not use the rate parameter. We simply use the average inter-arrival time for the exponential distribution. We assume that the first application arrives at time 0. So the system observation, the simulation will start when the first application arrives. So by that we assume that at time 0, the first application arrives, and each application in the loan office are going to be processed by these 4 steps in the following order, it says. So we have explained this, okay? So let me explain it again. First of all, we check the credit rating of the customer, but it says that this takes time, but everyone passes. So there is no one rejected at credit check step. We assume that, okay? Actually, in real life, this is not the case. You know, when you apply for a loan go to a bank, I mean, it is not guaranteed that you are going to have a credit. You can take a credit from that bank. It depends on your credit rating, okay? Now, after the credit rating is checked, then the loan covenant will be prepared, okay? The documentation will be prepared, and the officer at the first step is going to price the loan, which means the interest rate that you are going to be subject to or exposed to is going to be determined. And finally, you are going to take your money and leave, okay? Now, it says that each of these 4 steps have an exponentially distributed duration time with mean 1 hour, okay? So each 4 process here, they are independent from each other. And they are exponentially distributed. The process durations are exponentially distributed for each entity with a mean of 1 hour. And initially the system is empty and idle. So right now, when the first customer arrives at time 0, nobody is getting any service at any processes, okay? Also, this independence is valid between the inter-arrival times and the processing times. So whenever you arrive to this loan application office, it doesn't matter. You are always going to have an exponentially distributed service time in each of these processes. Okay. Now, we are going to develop a system where we have 4 officers. Okay, Alfie, Betty, Chuck, and Doris. So Alfie is going to be involved with the first process. Betty is going to be involved with the second process. Chuck and Doris are respectively going to be involved in the third and the fourth process. So these are the officers. These are the resources which are going to be used in these processes. Okay. And it says that all are equally qualified for any of the 4 steps. So Alfie is also capable of working in another process, or Betty is capable of working in another process as well. Now, in the first part, we are going to apply specialized serial processing, which means each officer will be used at each process. So Alfie will be involved with the first process in specialized serial processing. So once we go through Alfie, we are going to go through Betty in the second process. Then we are going to go through Chuck, and then we are going to go through Doris in the third and the fourth processes. Okay, so it is going to go like that. Then once we leave the fourth process, we are going to leave the system. However, there is this situation. For example, let's just say you have completed your credit check with Alfie, then it is not guaranteed that the second process will be idle. Okay, so right now, when you complete your process at the first process, it may be possible that there may be a queue accumulated in the second process. So in each process there will be a queue. Why? Because in each process there is a resource. As long as we have resources in the processes, there will always be queues. So this is the reason, my friends, this is the reason why I have explained this queuing theory and queuing systems to you 2 weeks ago. Okay. Why? Because in every discrete event system, we have queues. Why? As long as you have resources in the processes and these resources are limited, there will always be queues. Okay. So because of that system, real life discrete event system consists of multiple queues, sequential queues, parallel queues, etc. So in the second system, we are going to apply these processes as generalized parallel processing. And this, in the second system, this time each officer here, Alfie, Betty, Chuck, and Doris, are going to be involved with all of these processes for each client. So as a client, you are going to come to the loan office, loan application office, and when you find one of these 4 resources idle, either one of them, when you find one of these resources idle, then you are going to go through these 4 steps sequentially again, but this time all together with the same officer. Okay, so if you find Doris, for example, idle, then Doris is going to help you through all these 4 processes. And so in this case, we have generalized parallel processing. Why parallel? Because these 4 officers are working in parallel. So you can choose any parallel server, any one of them. And we say generalized. Why we say generalized? Because these officers are generalized in all of the processes here. So they can be capable of performing all of the processes here. Again, the durations of these processes are going to be exponentially distributed with mean 1 hour. But this time, since you are going to go with the same resource in all 4 processes, you are not going to wait in intermediate queues. Okay, so just in the beginning, you are going to wait in the queue until you find one of these resources idle, and then you are going to go through all these 4 processes with an 4 independent exponentially distributed time with mean 1 hour, and then you are going to depart from the service. So the question says that we are going to run the simulation models of these 2 models, both the specialized serial processing and generalized parallel processing, for 160 hours. Okay, and the single replication, it says. So the simulations are going to be very short, 160 hours per simulation, and one replication only. Okay, so this means what? If this is not going to be very long, and if we only have a single replication, most probably we are not going to get any confidence intervals in the statistical results that we are going to get. And then we are going to compare these two systems according to their performance metrics listed here, which I'm not going to read right now. So let's develop the simulation models first. After developing the simulation models, we are going to write these performance metrics one by one. Okay. Now, let's start arena. So remember, we have this run window here. Okay. So from this run, we are going to, so let me try to, my friends, okay. I think you are going to see arena better now with a larger scale. Please tell me so if you cannot see the desktop at the moment. Okay. I think you are supposed to see. Now, in this run window, we are going to go through setup, and in the setup, we first enter the project parameters, and the name of this project is going to be specialized serial. So this is the first part of the question. And the project description I can write here, so we need to say something here so another person who works with this project can understand what does this simulation model dealing with, what is it dealing with. And in the end of the experiment, we are going to get statistics related to entities, resources, queues, and maybe it may be a good idea if we get separate statistics related to processes, and we click apply here. So these are recorded. The name of the project is recorded. Now, this is the name of the project, but still I haven't saved the project file. Okay. And again, I need to save it as specialized serial here. And I'm going to save it on the desktop. Okay. Now, what I'm going to do is this. I am going to create an arrival process. Okay. First, and I will say that here, application arrives. Okay. So I have taken a create module from here and double clicked on that. And I said application arrived. This is the arrival process for me. And in this arrival process, I am going to change the name of the entities as, let's just say, applicants or application. Okay, application is the name of my entity. And the inter-arrival times are exponentially distributed. It is already selected as default with 1.25 hours average, right? And at each arrival, one entity arrives, one application arrives. And the number of arrivals is infinite at the moment. We are going to limit the simulation length by how? By from the simulation parameters, okay? Not from here. So the maximum number of arrivals is infinite. So as long as we do not terminate the simulation, the arrivals are going to continue infinitely. And the first creation is at time 0, so we can still write it here. And when we click OK, we are going to see our arrival process. Okay. Now let's click on run again, and in run from setup, we choose replication parameters. So in this simulation, the replication length will be 160 hours. Remember, this is the length of the simulation, and there will be only one replication. Okay? And the base time units is hours. So this means if we are going to enter any duration or any parameter in timely units, we need to enter everything in hourly units. Okay, so you do not enter anything in minutely or secondly or daily units, or base time units is hours in the simulation. Everything will be entered in timely units. So the replication parameters are introduced. Now I am going to add a process, the first process here. While the create module is selected, if you add a process, it will automatically connect it. So the first application that arrives is going to go through who? Alfie, right? So we need to change the name of this process. We say that Alfie checks credits. Okay, the name of the process is this. And what type of action do we have? Remember from the last week, seize, delay, release, we need to select. Why? Because every entity here are going to seize Alfie first and ask him to do the operation. So they are going to delay Alfie for a while. Then they are going to release Alfie and move to the next process. Okay. So seize, delay, release, we say, let's say, and we need to choose the resources which are going to be seized, of course. I mean, if you choose delay only, you see there is no resource here. But if you say seize, delay, release, or any other three options, so the question here is this: which resource is going to be seized, delayed, and released? And we need to add a resource here. So the resource name will be Alfie. Okay, Alfie will be seized, delayed, and released. And the units to seize and release, one. Everybody seizes a single Alfie, right? So actually there is a single Alfie already. Okay, there is only one Alfie. However, everybody here seizes one Alfie. Okay. For example, if you have multiple machines, you can seize multiple machines there. There may be 10 machines and you can seize 3 of them. So this is the question that is being asked here. How many units we are going to seize or release when we go through this process? Only one. Okay. So this does not indicate that there is one Alfie. Okay. Now, what is the delay type here? Remember, it is exponentially distributed. The process times are exponentially distributed with what? With 1 hour mean, right? So the units is hours here. It is already selected. So I need to write expo 1. So this indicates what? It's an exponential random variable with average 1, and because the time units here is selected as hours, then we are going to get our first process. So just like that, just like Alfie here, I am going to create another process. In the second process, we have Betty preparing the covenants. Betty prepares covenants. And again, we have a seize, delay, release operation, and we add a resource. The name of the resource is Betty, and one Betty is going to be seized here by each applicant. And expression, we have the delay amount as exponential in hours of 1 average, with average 1, and that's it. So you see we have 2 separate queues here. One queue in the credit checking queue process and one queue in covenant preparation process. Now let's move to the next process. So you can see it is automatically going to create connect the process to the last selected process. And in the third process, we have what? We have Chuck pricing loans, prices loans. And then we have seize, delay, release action here. And we add the name of the resource here, Chuck. And in this process, again, one Chuck will be seized by each entity. And the delay type is exponential again with an average of 1 hour. And finally, so you see there is another queue here about Chuck, about loan pricing process. And once this is selected, if I select process 4, automatically connected to Chuck pricing process. And in process 4, Doris disburses funds. Doris disburses funds, right? Okay, so we have a seize, delay, release type of action again, and the resource that we need to seize is Doris this time. And in this process, every client seizes 1 Doris, requires 1 Doris to do their jobs, okay? And again, the delay type is in hourly units, exponential with average one. Okay, so you see, as you create these 4 processes in the spreadsheet view, the processes are listed here. I mean, you can manually play around with the action types here and the resources that are going to be used as a list. So if you click on this row, for example, the resource required for this process is listed here. Okay, so instead of double clicking everything and change everything through the dialog box, you can also see these processes at the bottom. Okay, you can also see these processes at the bottom. And for example, you can change the expression expo1 here to expo2. So that is going to make the first processes duration with 2 hours of average exponentially distributed. Okay, so you can change everything from here as well. But one thing is missing here. What is that? The thing that is missing is the departure, right? So now these entities must leave the system. These entities must leave the system. So we are going to define, while Boris is selected here, we are going to introduce a dispose process, dispose module here. But let's just introduce it while Doris is not selected. As you can see, it is not connected, right? Automatically. So how do you connect it? If you want to connect it. So there is this connection here, connection tool, and you click from here and connect it to there, and then that is going to be connected. So at the disposal, we are saying that application departs here, and if you select record entity statistics here, the entities departure statistics will be collected. Now it is already clicked by default, so usually we do not change that because we want to see departure statistics as well. And we say, okay, so that is the simulation that we are going to create. Okay, now what we are going to do is this: we are just going to run the simulation. Okay, we are just going to run the simulation. And let's slow it down a little. So you see in Doris, there is a large queue here at Chuck. So let me show this like that. So right now, there is a single person waiting in the queue of Alfie's process, now 2. In Betty's process, there is nobody's waiting because most probably there is a very, very long process time, which is randomly generated at the process of Alfie. And here, at Betty, 1 person is getting a process now. But the longest queue we observe is at Doris. So this is not the thing that we are expecting, actually. I mean, I'm sorry, actually, we are expecting long queue size at each process, but sometimes it is going to be at Doris's process, sometimes it is going to be at Betty's process. If you get faster in simulation, for example, at some point Doris is going to eliminate her queue, and Chuck or Betty we are going to observe. So dynamically, the size of the queues are going to change. Sometimes we are going to observe long queues at Alfie. Okay, so that is the thing that we should observe. Okay, now I would like to see the simulation results because I am going to enter these values in the comparison table, benchmark table. I am going to compare the system with the generalized parallel processing system. So this is a 160 hours, as you can see here. This is a 160 hours of replication with a single replication here. It says the first of the 1 replications. So there is a single replication, and the first of these 1 replications has been completed, and you can see the results now. Now I would like to see the results here. Okay. And what are the questions that we need to answer? So for both serial and parallel processing systems, we need to answer these performance metrics. What is the average number of applications in process? So what is the average working process, it says. What is the average working process? So where do we check this? Through entity. Okay, entity. So because if you check the processes, the process statistics here is going to give the process statistics related to each process. Okay, but here the question asks, what average number of applications in process, which means the total process. So what is the average number of people in the system from the beginning to the end? And we can see such a statistic from entity part, entity section of the statistics. And in the entity section, you see we have work in process here, okay, at the bottom. Work in process. The average work in process in the system is 12.39, okay? So this means on the average, we observe 12.39 clients in the system. So actually there are four processes. However, we observe more clients than the processes on the average, 12.39. So what is the maximum? The maximum observed number of clients in the system in this 160 hours is 21. Okay, so we observed at most 21 clients in the system. What is the average time spent in the system by applications? Again, the time spent in the system by the applications, by the entities, can be seen in the total time here, and it is 16.08. So on the approximately, every entity here spends approximately 16 hours in the system. 16 hours in the system. I mean, even if you have the average process times are 4 hours, because you are waiting so long in the queues, a long amount of time in the queues, the average time spent in the system by each application is 16 hours. What is the maximum time spent in the system by any client in the simulation? The maximum value is observed as 27.21. So the longest waiting client has spent 27 hours in the system, okay? Average time spent in the queues by application. So the next performance metric that we are going to check is the average time spent in the queues by application. So we need to check here the waiting time. So the waiting time here is the average time spent in the queue, okay? So you see it is approximately 4 hours on the average, 4 hours smaller than the total time spent. 4 hours average, of course, not exactly, because the service times are random as well. So 11.98 is the average time spent in the queues. Now, if you check the queue statistics here, you are going to see the average time spent in each queue separately for each process, okay? Not just one by all of them. But if you sum all of these up, if you sum these all four values up, you are going to get exactly 11.98. Okay, so maximum time spent in the queues by applications. Again, if you check entity, an application here spends 22.27 hours in the queue. 22.27 hours in the queue at maximum. This is the longest waiting time in the queues. And how many? So the next question is this: number of applications completed in 160 hours. How many applications have been completed in 160 hours? So you see number out, okay, not number in. So right now, up to this point in 106 hours, 129 clients have entered the system, but only 117 of them have left the system with a successful completion of the processes. So this is 117. And the utilization of the resources, now we need to check the resource statistics. So as you can see, Alfie, Betty, Chuck, and Norris, they have a utilization rate here separately. So for all of them, we have a separate utilization rate. So how do we determine the average utilization? By taking the average of these four values, okay? By taking the average of these four values. But can we see the utilization in other ways? Actually, you can see it, okay? But I'm not going to explain this again. So you can determine the utilization by the queue lengths, okay? Queue lengths. You can determine the, not the queue lengths, but the number of people in the service process, so you can determine the utilization from there. However, let's just take the average of these four values. So here we have instantaneous utilization and we have scheduled utilization. Right now, as you can see, these two things are the same for the simple process, but in other type of simulations, they may be different. I'm going to explain the difference between the instantaneous and the scheduled utilization when the time comes. So you can check any of them, take the average of 4, and the result will be approximately equal to 0.78. So in this system, only in 78% of the time, the resources are busy, okay? They are not utilized completely in 100% of the time. So sometimes they weigh too much. Now, my friends, I haven't shown you in the practice, so I have just developed the simulation here, but let me show you. So we have spatialized serial here. These are uploaded in the LMS, actually. Now, I have developed a simulation model here in which where I see the resources busy idle statuses, okay, states. So how do you enter it? By you can, we have resource. So here we have resource animation. So you can relate each animation by introducing them. So you choose one of them and introduce it. And you relate it with the resource, any resource that you like. And when they are idle, they will become white. And when they are busy, they will become green. Okay. So, and also I have introduced two plot diagrams. In the first plot diagram, I will see the number of applications in each separate process. So with different colors here, you cannot see because of the resolution, but we have different colors here. We are going to observe the number of applications in each process in this plot diagram. Here, the total number of applications in the process. And so let's run this simulation at the slowest mode possible. So it says another model is currently running. So I need to close the other model. Yes. And let me expand this again. So as you can see, it starts. So let me make it a little faster. So you see, whenever a resource is busy, it turns the green, the light turns green. Okay. So whenever a process is busy, at other times they are idle. So if the light is red, white, they are idle. So the total number of applications in the process, so it has been increased to 22 or 21 here, as you see the maximum number of applications is observed here. So this is the statistics that we have collected. So the total number of applications in the system has a plot diagram like this in the simulation, and the applications in each process respectively is plotted here at Alfie, Betty, Chuck, and Doris. Okay. So let's make it a little faster and complete the simulation. As long as the animations are turned on, the simulation is going to be always slow, my friends. You need to completely turn off the animations, but the animations are very helpful. They are very helpful for us to see what's going on in the system, okay? So you see, this is the total number of applications in the system, and the average of this plot is 12.39. The average of this plot is 12 over 39. But you can easily see here there is a warm-up period here. So the system has not reached to a steady state because this is a serial processing system, and the system started first. First, Alfie has started working, but while Alfie is working, the other resources, the other officers were remaining idle, okay? But after a point of time in the system becomes full, okay? For example, after you observe the first departing client, the system becomes full, and after that, the system has reaches to a steady state. So if you include the statistics that you collect in the first 40 hours, for example, then you are going to get biased statistics. Now, the question here tells us to collect all statistics in the 160 hours, but I am explaining the danger of this thing here. So what we are interested in actually the utilization of our resources during the steady state, not in the beginning of the day. But in this system, in the beginning of the day, because Betty, Chuck, and Doris are not getting their clients immediately because Alfie needs to process first, then Betty, then, so Doris spends a lot of time, actually. Doris spends approximately 4 or 5 hours of time or 6 hours of time approximately. Actually, in the expectation, it is 4 hours, but sometimes it is more than 4, sometimes it is less than 4. So Doris needs to wait, I'm sorry, not 4, 3. So there are 3 processes before Doris. So for the first 3 hours, Doris does not get any client. Okay, so the actual queue behaviors can be observed in the the remaining part of the simulation. So it may be a good idea at this point. So let's show you that in the simulation we need to determine the warm-up period as 40 hours, and this means in the statistics that we are going to collect, these 40 hours are not going to be included. So we are just going to get statistics related to the remaining 120 hours. Now, I'm not going to do this because the question does not tell us something like that, but this is an important point. So I will close this application. And I am going to close this one as well and save that process. Now I am going to open another process, another project. And in that project, so not open, but new. In that project, again, from run window setup, we choose project parameters. The name will be generalized serial, generalized parallel. Okay, and again, we would like to collect statistics related to processes as well, even though we have not looked at them at all in the previous application. We can check it. Okay, so now again, from setup, replication parameters, we are going to have a replication length of 160 hours, 1 replication only, and the base time unit is hours. Warm-up period is going to be 0. And this time, we are going to develop a simple model, much more simpler model. Let's create the arrival process. So we say that application arrives here. And the entity that is arriving is an application. Okay. And the time between arrivals is exponentially distributed with an average 1.25 hours. And at each arrival, one entity arrives, the maximum number of arrivals is infinite, and the first creation is at time 0 again. So the arrival process has been introduced. Now, the next thing is a process. In this process, we have one of the officers processes all 4 steps. Processes all 4 steps. So you see in this process, actually there are 4 parallel servers. Okay, 4 parallel servers. And you need to seize, delay, and release one of these 4 parallel servers. Okay. So the resources are what? The resources are this time officers. So we say the resource, name of the resource is an officer. And how many units do you seize and release when you want to get a service? Only one of them, right? So you seize and release only one of them. But how many officers do we have? 4, right? We have Alfie, Betty, Chuck, and Doris. So we are going to change that. So the delay type is going to be what? Delay type is going to be an expression such as expo 1 plus expo 1 plus expo 1 plus expo 1. So why did we do that? Why have we written it like that? So because you are going to get all these 4 processes from a single officer, but each process is going to take an exponential amount of time with average 1 hour. Okay, so there are 4 independent sum of exponentials. Now we know from statistical modeling that another way of modeling this is this. So from build expression, you know, the sum of 4 exponential random variables, identical exponential random variables, is an Erlang random variable. So you can choose K Erlang from here, and you can say exponential mean is 1, and the Erlang parameter is 4. So the sum of 4 exponential random variables with average 1. So you can also choose it to write it like that, Erlang 1, 4. So both will work. Okay, in the book it says expo 1 plus, expo 1 plus, so and so forth. Okay, so now we shouldn't forget that there are 4 resources here. So how many officers do we have? So if you see here in resources, we have a fixed capacity during the whole simulation, and during the whole simulation there will be 4 officers. Okay, now if you click with right click on that button, and if you say edit via dialog box, you can also change that capacity from here. Okay, so remember, now with right clicks you can always open a dialog box. Okay, and in dialog box you can also ask these questions. So what is capacity here? If you click on that, it is going to explain you. So unfortunately the simulation model has terminated. There is a problem. Maybe I need to reinstall Arena. So let's check my prepared model. So there is only one more thing that I need to add here actually. So let me show again in basic processes the resource. From the resource spreadsheet view, I need to change the capacity of the officer. So the name of the resources here are loan officers. Now I have changed it to 4. And then I need to add a departure procedure connected to that, because anybody who leaves this process is going to depart. And if I double click on that, you can see that only the name should be written in a disposal module. Now I have a queue here, queue animation. Why? Because as long as we have resources in a process, we will see queue animations. Okay, so as you can see, there's only a single queue now. There's only a single queue. But if one of the officers are caught idle, you can take all 4 processes from one officer now. So the queue length is shorter actually, and the number of people in the system is also shorter. Now let's complete the simulation. So if you see all animations, it is going to be very slow. Now let's make it faster. So please check. How many people have left system this time? So in this design of the process, we have 135 people leaving the system, applications leaving the system. So we can immediately write that value here, 135. So actually, with the same randomnesses, even with the same randomnesses, we have served more than the number of we can serve in the other system design. Okay? And the average number of applications. Okay, so let's see the statistics here. Category overview. From reports, category overview. So here we need to check entity. So let's start the average number of applications in the process. It is 4.61, my friends. On the average, we observe 4.61 clients in the system, which is a lot better than the previous system. Maximum number of applications in process. The maximum number of applications in the process is 10, observed 10. So at most 10 people have been observed. Average time spent in the system by applications, total time is 5.38. So we have 5.38 here. And total time in the system, the maximum time spent in the system by applications is 30.73, as you can see.